I'm Leonardo Rolla, and I'll be leading this module ST342, Mathematics of Random Events. Before you start watching this video, you're strongly advised to read the study guide and read the corresponding parts of the lecture notes as indicated in the study guide. The goal of this video is to discuss why we want sigma additivity so badly. We'll start with some puzzling questions that will make us reconsider our understanding of probability theory, then discuss some relevant and interesting events that must be defined in some sort of limit, and then discuss the relationship between continuity and sigma additivity of probability measures. Let's start then with some puzzling questions. Can we toss a coin infinitely many times? Well, the first answer is, well, in practice, of course not. The age of the universe is finite, our lives are finite, we cannot toss a coin infinitely many times, but that's of course not the intent of the question. It's in theory, and in theory, what I'm asking is, can we define, does there exist this triple here called probability space? So does this mathematical object exist? An object where we can define a tossing of a coin that will come up heads with probability 1/2, will come up tails with probability 1/2, and define infinitely many copies of this instance in the same probability space, and so that they are all independent. The first answer to this question can be, of course, well, does it really matter? And, well, it does. It really does matter. We're not going to discuss so much in details at this point why it does matter. It will become clear throughout the module. Another question we may ask is, what is expectation? So we can say expectation is related to average or to the mean of a random variable, whatever that means. Or it can be the average outcome in the long run, in the sense that if we could repeat the experiment many times and we would add up the result, the outcome of these different instances and compute the average, this is what we would obtain. We could say that, but what is it? If we have a probability space and a random variable, what is the expectation? Then say, well, here's my random variable x, and if the random variable x is discrete, I compute the expectation of x by simply adding the numbers x that this random variable can take, multiplied by the probability that the random variable will take those numbers. And now if x is continuous, or let me insist here in the nomenclature, absolutely continuous, then we compute the expectation of x as an integral. We integrate the product of the number lowercase x by the density of the random variable evaluated at this variable, lowercase x. We integrate it against x on the real line, and this is the expectation. So the expectation is both an integral and a sum. But suppose I'm insisting, which one is it? The integral or the sum? And we insist on the answer that it is both. It will be an integral if the random variable belongs to one world, to one type of random variables, and it will be a sum if the random variable is of a different type. But then we have a serious problem if we insist that the expectation is both these two things. And the problem is, how can we possibly justify properties of this type? These are very general properties of the expectation, and they are very important, and we do use them in their full generality. And what is this? It says the expectation of the sum of two random variables equal the sum of the expectations of each of these random variables alone. And here, what it says is if we have two random variables on the same probability space, and we know that always the first random variable takes higher values than the second, then it will also have a higher expectation. This holds no matter what type x and y have. But so if x and y, they belong to different worlds, in quotation mark here, to different worlds, suppose the expectation of x is computed by one formula and the expectation of y computed by a different formula, how can we have any hope of justifying these two properties? Now let's talk about moment generating functions a little bit. Why are they called moment generating functions? Well, of course, because they generate moments, meaning if we compute the nth derivative of the moment generating function of a random variable and evaluate it at t or theta or whatever the parameter is called being 0, we obtain the nth moment of that random variable. And, well, why does it hold? Well, here we compute the nth derivative. Let's take the nth derivative of this expression, e to the tx. We know how to compute this derivative. We just get this x to the n outside. And now when we take t equals 0, this will be the exponential of 0. This is 1. And we got exactly what we were claiming. But, well, there's a little gap here in this argument. And the question is, can we really do that? Can we really do what exactly? Well, where can we have possibly a problem in this argumentation? Of course it is here, and it is, can we differentiate inside the expectation? Can we do that?